students. So welcome to our third lecture in this Chem 0902 electrochemistry course. Now we want to look at the Nernst equation, which was developed by Walter Nernst. And this equation, what it does is that it allows you to understand how the concentrations of the species in solution affect the cell potential. That is the potential that you measure on your voltmeter. Right? So let's say your electrolyte solutions are not 1 molar. What is the potential that you will get at the voltmeter? How can you calculate this? And this is what the Nernst equation is good for when you're working under non-standard conditions. What is the potential that you will get at the voltmeter? So of course we can still predict the potential of a cell given our knowledge of thermodynamics. Now there are some terms, for example, the Gibbs free energy that you know about already. For example, represented by G, H, and S, where G is the free energy, H is the enthalpy, and S is the entropy. And these are some important thermodynamic parameters. Generally, for any change in free energy in a system, delta G is equal to delta H minus T delta S, where delta G is a change in the free energy of the system and delta H is a change in the enthalpy of the system, whereas T is the temperature, of course in Kelvin, and delta S is a change in entropy. And these are all important parameters. Now also we can relate the free energy change under standard and non-standard conditions by the relationship given here, which says that the change in free energy, delta G, is equal to the change in the standard free energy, delta G naught, plus RT, where R is the universal gas constant, T is the temperature in Kelvin, and then we have now the natural log of the reaction quotient. Now, how do we make use of this? Okay, we'll see shortly. Now, the free energy change for a reaction, delta G, where you have that subscript R, gives a measure of the maximum useful work of a reaction, delta G W max. That's the maximum useful work of a reaction. Now, for a galvanic cell, this work is electrical work, right? Because we're dealing with an electrical system. Now, what can be used to run your cell phone battery, for example? Alright. Now, delta G subscript R gives a measure of the maximum work for a reaction, where delta G is equal to W max, maximum work. For a galvanic cell, this work is electrical work, right? Work that can be used to run your cell phone, for example. Okay, so the electrical work from a galvanic cell can run your cell phone. Now, it can be shown that delta G is equal to minus NFE, where N is the number of electrons, F is the Faraday constant, and E is the potential. Now, substituting for delta G in the expression on the previous slide, right? Here's the expression, delta G is equal to delta G naught plus RT ln Q. If we substitute for delta G, then we could have minus NFE is equal to minus NFE naught plus RT ln Q. Now, of course, we know that if we have a hypothetical reaction where we have reactant 1 reacting with 2 moles of reactant 2 to give us product 1 plus 3 moles of product 2, then the quotient is represented by this equation here on our right, where we have products over reactants, of course, raised to their coefficients. So, for example, reactant 2 is squared because there is a 2 beside reactant 2 in the reaction, and product 2 is cubed as a result of, or I should say due to the fact that there was a 3 beside it in the equation. Now, from equation 1 there, we could do a little bit of rearrangement. We could divide through by minus NFE, and by doing that, we have what we call the Nernst equation. Is E cell, and that E cell represents the potential that you would measure on your voltmeter, is equal to the standard cell potential, right, which is the potential calculated from E cathode minus E anode, as we discussed previously, minus RT over NF times the natural log of the reaction quotient Q. Now we could change from natural log to log using this conversion method seen here on the upper right hand corner of our slide to get now basically the same equation, but it's a little bit different because now we are using log. And we have E cell is equal to standard cell potential minus 2.303 RT over NF log Q. Now, if the temperature is 298 Kelvin, then what we find is that the RT divided by F times, of course, 2.303 will give us a value of 0.0592 over N, where N is the number of electrons, log Q, times log Q, of course. Now, at equilibrium, remember that at equilibrium, the cell will produce no potential, so your voltmeter will not be giving you anything, right? Because your cell is at equilibrium, the voltage is zero. Right? And that is what happens when you're, for example, your cell phone battery, you say that your cell phone battery is dead. It is just at equilibrium, and so you don't get a potential. Now, let's look at an actual example. Let's say you have a system where one of your half cells is a cadmium, alright, cadmium salt solution cell. So the cadmium, you'll have cadmium as an electrode. In this case, the cadmium half cell is the anodic half cell, where we have a solid cadmium electrode and we have a cadmium salt solution of concentration 0.010 molar. And on the right hand side, that is our cathodic half cell, we have the standard hydrogen electrode. Now the cell reaction is where we have cadmium solid being converted to cadmium 2 plus, that is an oxidation, that's a 2 electron process. That is, the cadmium solid will lose 2 electrons to produce cadmium 2 plus, and then now we have hydrogen ions, 2 moles of hydrogen ions reacting to produce 1 mole of hydrogen gas, and so of course those will require 2 electrons. It's a 2 electron process, that is, N in the Nernst equation will be 2. And the standard cell potential for this process is 0.40 volts. Now, here, Q for this reaction, right? Q, reaction quotient, is equal to concentration of cadmium 2 plus, right? Times the partial pressure of hydrogen gas, which is proportional to its concentration, divided by the concentration of hydrogen ions. And here we have the calculations, and the answer is 0.010. Alright, that is the value of Q, the reaction quotient. Now all we have to do is to plug all of that into the Nernst equation. We have Q, which is 0.010, so the log of Q times 0.0592 divided by 2. Right, and remember we explained just now why we have a 2 here, because N is 2, it's a 2 electron process. And you are given the standard cell potential as 0.40 volts. At the end of the calculations, you realize that the E cell is equal to 0.46 volts. And that's an example of how you make use of this. Here is an example that you can try, a zinc copper system, right? And here you have the concentrations, and you know already how to calculate the standard cell potential for a zinc copper system, as we did in the previous lectures. Now, there are many examples of electrochemical systems, and corrosion is an example of that. So metal corrosion is an electrochemical process, and it requires knowledge of the heterogeneous electron transfer kinetics. Heterogeneous meaning that you have a solution, right, and you have a solid, which is the metal, and the solution will aid the corrosion of the metal. Right, so let's look at how this works. Alright, let's look at, for example, oxidation of iron, which is what we call rusting, in a slightly acidic, aerated aqueous medium. So, solution is slightly acidic, and we have air present. So let's say you have a solid piece of iron and there's a droplet of water on the surface of that piece of iron. Now, you have a cathodic process and you have an anodic process occurring. Cathodic has to do with reduction, right? As we discussed previously, and anodic have to do with oxidation. And at the end of the day, we should produce iron oxide, which is what we call rust. Now, overall, initially, what you have is iron, right? Solid iron, as seen here in the first equation on our lower right-hand corner. Iron reacting with oxygen, right? And the iron, solid iron, is converted to iron 2 plus, and the oxygen in the presence of hydrogen ions, right, gets converted to water. Now, this redox reaction can be viewed as two partial reactions. So let's break it down. Let's look at it in pieces. Iron, right, will go to form iron 2 plus, so 2 moles of iron 0 goes to form 2 moles of iron 2 plus, and in so doing will produce 4 electrons. Think about it, because if 1 mole of iron, right, if 1 mole of iron gets converted to 1 mole of iron 2 plus, to go from iron 0 to 2 plus means that you lost 2 electrons, right? But if we're looking at 2 moles of iron, then we will get 4 electrons, and the potential for that is minus 0.44 volts. That's an anodic process. Anodic meaning oxidation, because oxidation occurs at anode, as discussed previously. On the cathodic side, what you have is oxygen gas, right, reacting with hydrogen ions, 4 moles of hydrogen ions, and 4 moles of electrons to produce 2 moles of water. And the potential for that process is 1.23 volts. And that's a cathodic process because it's a reduction. That is, oxygen and hydrogen ions accept electrons, and these electrons are coming from the anodic process. Subsequent reactions will happen, of course, where you have iron 2, right? So the subsequent reactions that will occur is where iron 2 will react with oxygen to be converted, or therefore allowing conversion to iron 3 plus. Okay, right. So iron 3 plus in the presence of water. Now iron 3 plus will then react with more water to produce iron oxide, right? It will react to produce iron 3 oxide, which is hydrated, and also 6 moles of protons. This iron 3 oxide, hydrated, is what we refer to as rust. So that is how it is produced. Of course, you would probably need to go back over these equations and follow the process sequentially to get a better understanding. That's basically what it comes down to. Now, corrosion, of course, is oxidative deterioration of metal. For example, corrosion of iron, as we just discussed. Now, as you saw in the case of iron, the reaction is very favorable in acidic media. Now, the reaction is still spontaneous under neutral conditions, right, where pH is 7, and even under basic conditions, where pH is above 7. So it still occurs. So it occurs in acidic media, neutral, or even basic. Of course, in basic media, the reaction mechanism and the steps involved are a little bit different, but at the end, you get the same results. Now, the processes occurring can be represented by a galvanic cell. Electrons are supplied at the cathodic region from the more easily oxidized anodic regions. And the circuit is completed by the migration of ions in water droplet. That is, iron 2 migrates from where it is formed in solution and is further oxidized by dissolved oxygen to form iron 3. Now, corrosion. Now, of course, metals are very important to the global economy, or to the economies that make up the globe, because metals are used a lot in ensuring the structural integrity of buildings, for the manufacturing of storage tanks, and even for making vehicles that we use for transport, trains, ships, aircrafts, cars, so on and so forth. Now, it is therefore important then that we are able to control the rate of corrosion, right? We cannot stop it totally, because it will eventually happen, but at least we can control the rate of this process. Now, we can use a method called cathodic protection, that is protecting a metal by connecting a second metal that is a sacrificial anode. Let's see what we are talking about this, where we mentioned this sacrificial anode. Now, a sacrificial anode is a metal connected by insulated wires to the metal that is to be protected. And the sacrificial anode is therefore corroded preferentially. Right? Because remember, if you have two metals and one is more reactive than the other, the one that is most reactive will react before the less reactive one. So that is the basic principle behind the entire thing. Alright? So if you have two metals, one would rather to undergo oxidation, whereas the other will more likely undergo reduction. The one that is more that will react faster to oxidation will undergo oxidation. That's the basic principle. And we'll mention it again. Now, so if the sacrificial anode is to be corroded preferentially, think about it. What is the requirement in terms of E0 relative to the metal to be protected? Well, E0 of the sacrificial anode must be more negative than the metal that is to be protected. So if you have two metals, you want to protect metal A, you have to ensure that metal B has a more negative E0 value, such that in the presence of oxygen, metal B will react and undergo oxidation, right, rather than your metal to be protected. Think about it. Now, this is an example, a very nice example where we have zinc, right? Zinc metal protecting iron metal. Now, zinc would undergo oxidation faster than iron metal, or preferentially, if you are comparing zinc to iron metal. Zinc will undergo oxidation because iron is about what? Minus 0.44 volts, whereas zinc is minus 0.76 volts in terms of their reduction potentials. And so what you find is that zinc will more likely to undergo this oxidation compared to iron metal. So we have to check. We have to check those potentials. Check the potential for the reduction of iron 2 versus the reduction of zinc. Just check those potentials. So those numbers I threw out a while ago were just off the top. So we have to verify those, make sure. Alright? So this is an example of zinc being used to protect iron metal. No, note that the sacrificial anode may be used as a protective layer as shown above. So the iron metal could be coated with zinc. Okay? However, after some time, the zinc layer could be get eaten away, and then the iron start to oxidize. So what we have done is to slow down the process. Alright, not totally prevent it, but slow down the process. So the iron metal will only start to undergo oxidation after the zinc layer has been eaten away by oxidation, or if there's a scratch. Another good example of this is, let's say you have to, you're building a rig, right? You're building a rig, and that rig is supported by metals. The rig is in the sea, right? Seawater is around the metal support beams of the rig. You will need to protect these support beams by connecting them to something like an aluminum anode, right? Aluminum is more reactive, right? That is, aluminum will rather to undergo oxidation much more than, say, the steel that holds your rig together. And so what you find is that the aluminum metal will undergo oxidation, right, sacrificially, therefore allowing your rig to be able to maintain its structural integrity whilst out there in the seawater. So that's just an example, an everyday example that we could relate to.